All right, next up we have Trisha Mahoney on removing unfair bias in the machine learning pipeline. Trisha Mahoney is a Trisha Mahoney is a technical evangelist for machine learning and AI at IBM. Trisha has spent the last 9 years working in high-tech firms doing product management and marketing roles in AI and cloud at IBM, Salesforce, Cisco, and Smiths Group. Prior to that, Trisha spent 8 years working as a data scientist in the chemical detection space. She holds an electrical engineering degree and an MBA in technology management. Please welcome Trisha.
Okay. Hopefully that's high enough. Okay. Hi, everyone. Just checking if you can hear me okay. Yes? Okay. All right. So today, I only have 25 minutes, so I was going to do kind of an intro to fairness and bias, go through some of the fairness metrics and algorithms, and a few fairness guidelines. And typically I do a Python tutorial, but we have 25 minutes today, so I'll do an interactive demo so you can look at how we use the AI Fairness 360 toolkit in sort of a visual form. And then I'll go a little bit into how we've integrated this open source toolkit into our products so you can debias in your pipeline. Okay, so why do we care about fairness? We know that human decision making is flawed in many ways, and it's shaped by people's and society's biases. And these are often unconscious. So everyone assumed that when we started to use data to automate decisions, everything would be fair. But we now know that's not the case. Evidence has shown that AI can embed our own human bias and deploy them at scale. And many experts are now saying that bias may be the major barrier that prevents AI from reaching its full potential. So today we want to talk about how do we ensure that automated decisions are less biased than human decision making. So first we have to look at what is fairness. This sounds like an easy question, but how do companies and industries even define this for their business problem? There are over 21 mathematical definitions of fairness, and these are not just theoretical differences in how to measure fairness, but they're different definitions that produce entirely different outcomes for your algorithms. So there isn't a one-size-fits-all. You really have to define this for your organization and for each use case. So, data scientists have to start kind of moving beyond kind of our prediction accuracy and talking with our stakeholders about how do we define this. So just as an example, work has been done by two leading researchers who found bias when you Google search the word CEO. Only 11% of the top image results showed women as CEOs, but women were actually 27% of US CEOs at the time. So, how should or how would you determine the fair percentage of women CEOs an algorithm should show? Is it the percentage of female CEOs we have today, 27%, or should the fair number be 50%, even though this isn't the reality of today's world? So, in my mind, I thought logically it should be accurate. It should be 27%, right? But if anyone were to take a vote, what would you say, 50%? Or should it be 27%? 50, okay. To me, I thought 27%, but when I looked at, kids searching on Google to see what a CEO is for the first time, and they see 90% male images, you start to see how we can actually create bias, with the amount of images that they see. So, this is a common scenario brought up in many talks, but you may have heard of an algorithm called COMPAS, which was used to predict whether prisoners in Florida were likely to commit another crime if they were to go on parole. It was later investigated by ProPublica and found that the COMPAS algorithm incorrectly labeled African American defendants as high risk at nearly twice the rate it mislabeled white defendants. So this, got a lot of buzz in the news. What you don't often hear about is that COMPAS actually tried to eliminate gender and racial bias from the start. The company that developed the COMPAS scores claimed that its system was unbiased because it satisfied predictive parity, but ProPublica found that the algorithm was biased because it did not demonstrate balance for the false positives. So, they didn't go out trying to build a biased algorithm. It was the way they defined fairness that inadvertently kept many African Americans from going on parole and home to their families. Another example is Amazon's recruiting tool, which recently had to be scrapped. Amazon's models were trained to vet applicants by observing patterns in resumes submitted over a 10-year period, resumes which predominantly came from men due to hiring decisions that were made and just the candidate pool in general. The algorithm actually taught itself that male candidates were preferable, and it penalized resumes that included words such as women's chess club captain, and it downgraded graduates of many all-women's colleges. So, I think the point was Amazon tried to remove the bias after the point, but they could not due to the complexity, so they had to scrap that. So today what we want to talk about is AI Fairness 360. It's a comprehensive open source toolkit for detecting, understanding, and mitigating unwanted bias. This was built by a lot of IBM researchers, but it's comprised of Python libraries with over 77 fairness metrics, 10 bias mitigation algorithms, and fairness explainers. So this is, the research from academia and industry from all over the world. It's not just an IBM thing. These are kind of the cutting edge fairness bias mitigation techniques. So what they wanted to do is really provide data scientists and practitioners access to these things that were in research, and there was no available way to implement these things in your pipeline. But before we jump into the toolkit, I'm going to just talk to you quickly about where bias comes from and how you measure it. So, we often hear of algorithmic bias, but the underlying data are often the main source of bias, not the algorithm. So this can occur due to over or undersampling, label bias, and user-generated bias. So our models are really trained on data from, past human decisions over many decades, which can reflect societal and historical inequities. So let's look at a selection bias case where one population is overrepresented in a training data set. MIT recently identified this problem with the top facial recognition services, which had been trained on predominantly white male data sets. This resulted in a 99% accuracy for lighter skinned males and a 65% accuracy for darker skinned females. So you can imagine what the implications may be when governments use surveillance technologies and you're a darker skinned individual. So, I see a lot of this question comes up in a lot of our from our customers from different communities, and they ask why we can't just drop protected attributes such as race, age, or gender. And you can't drop these protected attributes because there are many features that are too closely correlated. Even if you look at something as benign as zip codes, it's actually very easy to deconstruct an individual's race or income by analyzing this data. And this is just a map of New York City, Brooklyn, New York from 1977 when banks used something called redlining, which was actually legal, to discriminate potential customers by zip code. So, the lenders were providing different amounts of credit in areas based on different ethnicities. And so you can't do this today, but it just shows you how easy this is to do. So, before I jump into the demo, I wanted to go through a few terms that are different than a typical machine learning pipeline that you would need to know. So one is a protected attribute. You do have to define this in your model in order to measure and remove bias. So this is something that partitions populations into groups whose outcomes should have parity. So, for example, race, gender, caste, and religion. Privilege protected attribute is an attribute indicating a group that has historically been at a systemic advantage. And then group fairness and individual fairness, I'll talk a little bit about this, where you have to define this at the very top for your use case. This would be group fairness, groups defined by protected attributes receiving similar outcomes, and individual fairness would be, we're all treated equally and should have, the same types of predictions or outcomes. And then the fairness metrics are really how we measure bias itself. And you'll see that there are favorable labels that correspond to an advantage to a specific privilege class. So within the toolkit, there are over 77 metrics. And I'm just going to demonstrate, talk about 3 here, but you really should use as many as possible that are applicable to your use case. And that's kind of the mistake that Compass made when they were deploying their algorithm. So the first is statistical parity difference. And really, this is the difference in favorable outcomes received by an unprivileged group to that of a privileged group. Disparate impact is the same favorable outcomes rate for unprivileged versus privileged, but this is really just a ratio. So for statistical parity, you want to get this as close to 0 as possible, and that shows that you have reduced bias. Disparate impact as a ratio, you want to get that as close to 1 as possible. And equal opportunity difference is also widely used in the industry for fairness, and that's the true positive rate of the unprivileged class to the privileged class. So just going back to the question of how you define fairness and how this impacts how you measure bias. So if we look at what seems like a simple question, if you're a university, do SAT scores correctly compare the ability of my applicants? So your university may believe, yes, I believe in individual fairness. SAT scores correlate well with the future success and correctly compare the ability of my applicants. This is just an example of metrics you would use. But if you were to say no, I'm in the School of Engineering, the SAT scores actually may contain some structural bias. So its distribution may be different across groups, right? It may be different for women if you're the School of Engineering, kids that are lower income, or minority groups. So really, depending on how you define this, it's really going to change the way you apply the algorithms and metrics. So this is kind of a view, blue is where the toolkit kind of can serve in your pipeline, and bias can occur at any stage throughout your pipeline. And fairness metrics and debiasing algorithms can be performed at various stages of your pipeline. So it's recommended to check for bias as often as possible using as many metrics that are relevant to your application. It's also recommended that you integrate bias detection into your automated pipeline to ensure that you're continually correcting for bias. And so, a lot of the question of which algorithms you use is where you can intervene in the pipeline. And we have a lot of consultants that work with our customers, and they can't actually get access to the data. They don't know what the protected attributes are. So if you can modify the training data, then you can use pre-processing. If you can modify the learning algorithm, then in-processing can be used. And if you can only treat the learn model as a black box and can't modify the training data or learning algorithm, then only post-processing algorithms can be used. So the AI Fairness 360 toolkit includes 10 algorithms across each phase of the machine learning pipeline, and there are several more algorithms coming down the pipe. And this is just important to remember. Again, it's an open source toolkit. It's comprised of the top bias mitigation algorithms across many different researchers from academia and industry. So it isn't just an IBM thing. If you were to kind of search for a lot of the libraries out there for bias mitigation, most of those libraries were pulled into this toolkit, and it's an easier way for you to implement them into your pipeline. So, the main guidance, as bias starts with our data mostly, is pre-processing is the optimal time to mitigate the bias. So there's a little bit of guidance around this. For pre-processing algorithms, reweighing only changes the weights applied to training samples. It doesn't change any features or label values. So this is a good option if you're unable to make value changes. Disparate impact remover and optimizing pre-processing yield modified data sets in the same space as the input training data. So if your application requires transparency, then these two are a good option. And learning fair representations modify the data set in the latent space. So, as you're going to see in the demo, there are a lot of trade-offs between bias and accuracy. I see some talks that argue that you can still retain your prediction accuracy if you remove bias, and a lot of people say they don't want to touch it because it's going to, lower their prediction accuracy. However, I think models learn from the data that we give it, so we're responsible for building a fair set of data. So it's really a question of thinking about what your model is doing, if you're doing good things or bad things to people. If your model's sending people to jail, maybe it's better to have more false positives than false negatives. And if your model's handing out loans, maybe it's better to have more false negatives than false positives. So really, you and your stakeholders have to determine the thresholds that you guys can handle as an organization for accuracy versus fairness. And this is based upon your legal, ethical, and trust guidelines. So, I would say doing what's legal is preferred, is the top priority. And then, there's huge penalties for that, as we're seeing with a lot of algorithms. And doing what's ethical, I use Amazon Echo as an example. It wasn't illegal to kind of record people at all times, but it wasn't ethical. It didn't look good. And then, thinking about trust, like if I use Facebook as an example, they lost trust in a lot of users. So, the cost for losing trust and trying to regain those users is great. And so, just to be kind of open on this, preventing bias is hard. And I'll just start with this caveat here. The AI Fairness 360 toolkit should only be used with well-defined data sets and well-defined use cases. But, the ask is to really work with your stakeholders early to define fairness, your protected attributes, and the thresholds between accuracy and bias. And again, applying the earliest mitigation in your pipeline as possible that you have permission to apply. And checking for bias as often as possible using any metrics that are applicable are the main things. So I'm just going to quickly show you where the toolkit is. Oops. So this would be the main page of the toolkit. You can do demos. There are a lot of research papers on this, and there are specific Python tutorials you can use. But, each notebook is here on every algorithm, and not all of the metrics are here. But I think one of the important things is the API documentation. As these become very complex, you can kind of go into each algorithm, look at the research paper that it was built on, and kind of look at the code and the parameters. And I think the API is a good way to guide you through understanding a lot of these algorithms. And this is for the pre-processing, in-processing, post-processing. There are data sets that you can use to experiment with, as well as explainers, which is being built out more. Really explaining to you what each metric means is important, and as well as all of the code behind the metrics as well. So I wanted to do sort of a quick demo. I know this is very short, but I wanted you to see, if we look at the compass algorithm again, we're just going to run through a data set and apply a few algorithms visually. So here, again, the protected attributes are sex and race. And for the criminal justice system, privileged is actually female and unprivileged is male. And for race, we have Caucasian or not Caucasian. So if we were to check for bias, you'll see there are about 5 different metrics here, and you can see what each one means. But the prediction accuracy is 66%, and you can see in the red here for sex and for race, there is bias in this red area. It's not within our threshold. So what we want to do is look at the reweighing, which is a pre-processing algorithm, and apply that. And when I do that, we see that the original bias was here, and for sex, we got the bias down to 0, much closer to 0. So you may be doing this in code, but we're just kind of visualizing what this looks like. And the prediction accuracy just went down a bit. So across these metrics, for race or sex, you can see that we've reduced bias significantly with that algorithm. However, if we were to try to apply the algorithm for the classifier doing in-processing, you'll see that there's a very different result. And as you can see here, there is still bias significantly across sex, although bias has been removed in terms of race. So what this shows is, if you try to use a different algorithm or a different technique, you're actually biasing against men in the criminal justice system, which is unfair. You can't really look at two people and say, because you're a man, you're more likely to commit a crime and you need to stay in jail. That's where I think human bias and judgment may come in, but we want to make sure our algorithms are making things more fair for those that it impacts. This is open source right now, and we're starting to integrate this into Watson OpenScale and a lot of our Watson products. It's still early stages, but for models that are in production, we do have Watson OpenScale, and basically you're able to automatically monitor bias from correlated attributes in a model. You can visualize deployed models' fairness, and you can see it quickly inside your production deployments. And you're able to select favorable and unfavorable populations for privileged and unprivileged classes. So if I were to go into Watson's OpenScale, sorry, I'm jumping around here. You can see this is a German credit risk model, and it's basically looking at the credit worthiness of basically your customers, right? And what they found is that there is some bias against women, as more men are applying for credit. But as a business person, you don't want to have that bias there. You want to make sure you're actually going to make more money by not being biased. So, for a production model, you can look at a certain time period, that you can set your thresholds, you can look at age versus sex, and you can see all along the line here, what is this threshold of fairness, the fairness score that we're hitting. And if it does get below a certain threshold, we know that we need to ensure that we can correct that bias. So if you guys want to learn more, it would be good to join the external Slack channel for AI Fairness 360. There are a lot of researchers there to answer your questions. And I'll be on there as well. There's people who need help with the Python installation. Some people need research papers. A lot of people ask questions, how do I define my protected attributes? There are a lot of complexities. It's very broad. So if you do need to ask those types of questions in terms of getting started with your business, this would be a good place to start. We're currently starting to work with really large customers right now, B of A, ING, for example, and trying to tackle some of their bias complexities, which they're big companies, so it's going to take a while to do.